So this will be a three-part series, and in this first part we're going to find the reaction forces. In part 2 we're going to do a shear force diagram, and in part 3 we're going to do the bending moment diagram. So let's find the reaction forces. So here we have the UDL that is spread across the entire beam, and we also have 3 additional point loads, and we're going to take the moment about RA. So we're going to pivot about this point right there, highlighted in red. And the system I like to use is to say clockwise moment is equal to counterclockwise moment. And then I look at the forces to see what's going to try and pivot the system clockwise. So the first force here, we have that 5 kilonewtons, and it's 4 meters away from our pivot point. So we're going to find the moment about that point, and the formula that we use for moment is force multiplied by perpendicular distance. So our first force being 5 kilonewtons, and that's 4 meters away from our pivot point. Next we go over to the 19 kilonewtons, and we're going to sum that, and the 19 kilonewtons is still trying to pivot like that. So we're going to take that to be a clockwise moment again. So we're going to have 19 multiplied by its distance, which is 9 meters. Going across again, this time I'm going to focus on the UDL. And for the UDL, we're going to first convert the UDL into a point load. So what we have there is 2 kilonewtons per meter. So that's 2 kilonewtons per meter, and it's spread across 18 meters. So that's the first part. Now we have to do another multiplication because this force, or 2 times 18, is our total moment, and we need to convert that into a point load and place all of that now into the center, which is why we're going to halve the length. So this 18, we're just going to half it down the middle and place that 36 kilonewton meters right there. So it's 2 times 18 times 9, and that would take care of our UDL. So the next force that we have, again, that's trying to pivot this way, which is clockwise, is our 3 kilonewtons. So that's going to be plus 3 times its distance, which is 14 meters. And those are all the forces that are trying to pivot in a clockwise moment. So if we look at RB now, RB is trying to counter all of that, going in that direction. So RB is going to be on our counterclockwise moment side. So it's RB multiplied by the total distance, that is 18 meters. So all that left to do now is to just sum everything up and solve for RB. So when we do that, we get our 20 there, 19 times 9, we get our 171, 2 times 18, 36, times 9, we get our 324, and finally 3 times 14, we get our 42. And all of that is equal to RB times 18. So to cut to the chase, we're going to sum all of what we have on the left side and divide by our 18 for RB. So we're just rearranging this here now to make RB the subject. So that's 557 divided by 18. And that gives us our 30.94 kilonewton. So that's the reaction force there at RB. So the next step in our equation is to find our RA, and to do that we're just going to say that our upward vertical forces should sum to be the same as our downward vertical forces. So what we have going up, we have our RA plus we have our RB, and what we have going down, the actual forces, that's what we're going to sum up. So just take another look. So we have that 5 kilonewtons plus, that's 19, plus 3, and this 2 times 8 is for our UDL. So plus 2 times 18 gives us the UDL. And what we need to do, we need to sum all of what's on the right and subtract that known value for RB. So then that looks like so. So RA is equal to all of what's on the right. That's going to add up to 63 kilonewtons. And we're going to subtract our RB value, which is 30.94. So we get our RA to be 32.06 kilonewtons. So that's the reaction forces for RB and RA completed. Now the next step for us is we're going to draw our shear force diagram, and to watch that process, just check out the next video here and I'll see you over there.